Welcome to my channel. Before I get into today's problem, I just wanted to give a quick apologies. The uploads of these videos are a bit inconsistent, and that's because I'm still working a full-time software engineering job, so it does take some time to juggle both of these. That being said, let's jump right into it. I wanted to go over a very simple, yet somehow a complicated problem, apparently. This is validate binary search tree. This is BST. You're given a tree and you have to check to see if it is a valid binary search tree. And you know what? A lot of people actually screw this up. This is a common question I ask in my phone screen. Typically, when this question is asked, there's like a second question. People expect you to do this in 15 to 20 minutes and then move on to the next question in the phone screen. Honestly, I've seen even Google guys screw this up, and that's very surprising. I looked online and I see on Stack Overflow solutions that are just way too long and way too complicated. I don't even think this is working. Other solutions that trying to add and build upon that. And then there's like an in-order solution. I actually like this solution. This is pretty cool. You use in-order traversal, and then in another for loop pass, you check all the values. But again, this is not the most efficient because you're not exiting out when you immediately find that it's not a BST. I've even seen people pull out stacks to solve this problem. And honestly, this just seems not intuitive. I don't think people can pull out stacks to solve this and get the solution working on the first attempt. It just never happens. I've never seen it. By the way, I found this on Geeks for Geeks, and honestly, I just do not trust Geeks for Geeks. Let's dive right into this. I've drawn out a tree here. Basically, here, all the children to the left of root must be less than the root, and all the children to the right of the root must be greater than the root. And when I say root, I mean the value of the root. This is a valid BST. This is also a valid BST. It fits the definition of a binary search tree. This, however, is not a BST. As you can see, 4 here is to the left of its root and it is greater, so this violates the definition. If you take a look at this example, you can see this is also not a BST. Even though 3 is less than its immediate root of 6, it is less than 5, even though 3 is to the right of 5. The best way to solve this question is to use boundaries. So when we introduce the concept of lower bound and upper bound, you'll see that this becomes pretty simple. When we start at our root, the upper bound here is infinity and the lower bound is negative infinity. That means we can choose any value in this range to be our very first root, which is 5 in this example. And as we go on into the recursion, when we go left, notice that we are changing our upper bound. So essentially any value you see here should be between this new lower bound and upper bound, and 1 fits that bill. So we're good here. So move to 6, you can see that we've changed our lower bound now, and 6 fits into this lower and upper bound. Our lower bound has changed to 6, but 16 still fits the bill, so we're good. And now finally we're at 3. This violates our upper and lower bounds. 3 is not in range. So this is why this is not a BST. This is like the dead simple pseudocode here. We have a simple check here that checks to see if our values are within the bounds. And if they're not, then just return false. And that's it. That's really it. This is so simple. I've written the code out. This is exactly what we have discussed. And in the worst case scenario, this solution is an O of n time complexity. And in the best case, we can actually do better than O of n because we return early if this is false. I'm going to go ahead and submit this. And boom, we've got it.